All right, let's get started then. I'm talking about our polynomial functions. So first thing, I do need you to write down the stuff on this slide. Do you want me to just let you write and then I'll talk about it? Okay. You can abbreviate whatever makes sense to you, but those are the two pieces you need down. So the first thing on here, the conjugate zeros theorem. This is telling us something about our zeros. We know zeros, we've talked about them a little bit. We know a zero is a number. In terms of a graph, it's an x-intercept. It's where a graph hits the x-axis. In terms of like our polynomial, it's the number that makes it equal 0. And what we've looked at previously is just real number zeros. But we've solved quadratic equations that had imaginary zeros before, right? So we know they can happen. Well, it turns out that if you have a polynomial and all the coefficients are real numbers, so you're looking at a typical looking polynomial, there's no i's in it. If you have one imaginary zero, the conjugate will also work. So the imaginary zeros come in pairs. If you have one, the conjugate will also work. Remember, the conjugate just changes the sign on the I portion. Second thing, we've talked about this a few times. I keep telling you we need to know that. Multiplicity is just the number of times the zero occurs. So today, we are really just going to practice this conjugate zeros theorem and look at a couple different situations where we encounter that. Does everyone have the stuff down? Okay. So, for example, I want to create a polynomial where 3 and 4 plus I are zeros. All right, last week we talked a lot about the difference between a zero and a factor. If 3 is a zero, what's the factor? X minus 3. Okay, I only gave you 2 zeros. But if 4 plus I is a zero, what else has to be? We just said if you have one imaginary zero, the conjugate will also work. So if I told you 4 plus I works, we know 4 minus I is also going to work. So I add that to my list. So my factored form will actually have 3 parentheses. Okay, in the factored form, it's always x minus these things. So it'll be x minus 4 minus I and x minus 4 plus I. Does the order of the parentheses matter? No, not a bit. So it's x minus the 4 plus I and the 4 minus I. You notice the only difference between these last two parentheses are the i's have opposite signs. That's because they're conjugates. If you chose to spend the time multiplying all this out, we would end up with I squared, and what does that turn into? -1. And so the actual polynomial, when it's multiplied out, wouldn't have any i's in it, but it factors this way. All right, let's do this one. So I want to create a polynomial where -2, 5i, and -1 minus I are zeros. So first question is, do I need to add any zeros to the list? Yeah. Do I have to add anything else to go with the -2? No, because it's not imaginary. If 5i is a zero, what else has to be? If -1 minus I is a zero, what else has to be? So I should have 5 parentheses here. If -2 is a zero, what's my factor? Right, so it's the opposite sign. So 5i is a zero, we have x minus 5i. -5i is a zero, x plus 5i. What are my other two parentheses going to be? Except since it's already a -1, it'll have to be +1. So that's the opposite. So when I plug this in, it equals 0. Again, order doesn't matter. We just need all this. So what I want on these questions, I'm checking to see, do you recognize if I give you an imaginary 0, the conjugate also works? And can you take a 0 and write the factor, which is just the opposite sign? Any questions on those? Okay. Let's try another question. I want to find a polynomial of degree 3, so that means if I multiply it out, it's the third power, that meets these requirements. First one, the zeros are -3, -2, and 5 plus u. If it's degree 3, we should have 3 zeros, and I gave you all 3 of them. None of them are imaginary, so I don't have to add anything else to the list. So if I'm writing my polynomial, if -3 is a 0, what would my factor be? If -2 is a 0. If 5 is a 0. Okay. So I've got the degree 3, I've got my zeros. Then I give you this thing. That tells me if I plug in -1, this has to equal 6. If I put in a -1 for my x, -1 plus 3 is 2, -1 plus 2 is 1, -1 minus 5 is -6. So all I did is I plugged in my -1. If I multiply that, that's -12. That doesn't equal 6. It's only degree 3, so I can't have any other x's in here. The only thing I could have is a number in front. This whole thing could be multiplied by a 3 or something like that. So let's see what that number might be. Let's say I just call it a. I know when I plug in those numbers, I need it to equal 6. So this means -12a has to equal 6. If I divide by -12, my a is -1/2. So to get it to be 6, I need to multiply by -1/2. So my whole polynomial has a -1/2 in front. And I needed that just because I gave you all the requirements I wanted you to satisfy. Okay, if I hadn't given you this thing in the box, would I need a number in front? No. Did I lose anybody on that one? Let's try another like that. Four is a 0. If 4 is a 0, what do I have to have in here? Of multiplicity 3. What does that tell me? So you could write x minus 4 3 times. You could also just put it to the third power. So the multiplicity is the number of times it works. Either write your parentheses repeatedly or use it as an exponent. So I have my degree 3, I have my 0. The other thing, when I plug in a 2, it has to equal -24. So the only other thing I could have, I can't have any more x's, I could have a number in front. So let's see. If I put in 2, I need this to equal -24. So that's -2 cubed, so -8a equals -24. So a is 3. So for this to work, it has to be multiplied by 3. questions on that? Do we need additional practice with diagrams? So there were 3 things I wanted to do today. We just did 2 types of problems. One final type. We're going to do a few of these until we get the hang of it. Remember last week, we were factoring our polynomials and I would give you the first 0. We're doing the same thing, but this time the first 0 is an imaginary number. Okay, so I want to find all the complex zeros. If I say they're complex zeros, that means they could be real numbers, they could be imaginary, or some of both. Given that 3i is a 0. How many zeros should this have? You guys know? 4. How'd you know that? The highest exponent. The degree, the highest exponent, that's how many zeros? I gave you one of them. We have to find the other 3. Okay, so think back to last week. When I gave you the first 0, what did we do with it? Synthetic division. All right. I would recommend spacing this out just a little bit more than your typical synthetic division. On these, when you're doing synthetic with an imaginary number, the first one is the ugliest. After that, everything gets prettier, I promise. What do I know I should get as a remainder when I do this? 0. Okay, so synthetic. First number comes all the way down. 1 times 3i is 3i. Are these like terms? No, so when I add them, it's just -1 plus 3i. Okay, this is where it gets a little bit ugly. You can come out to the side and multiply it. I take 3i times -1 plus 3i. So when I do that, I get -3i plus 9i squared. But what is 9i squared? I squared is -1, so 9i squared turns into -9. So we have a little more work with multiplying, but we have multiplied imaginary numbers before, so it's nothing we haven't done. So when I add, I can add the 10 and the -9, so I get 1 minus 3i. So then we have to multiply 3i times 1 minus 3i. So we get 3i minus 9i squared. What is -9i squared? 9. So this is 3i plus 9. When I add, -9 and positive 9 cancel, so we just get 3i. So final step, we have 3i times 3i, which is 9i squared, or -9. And that gives me a 0. All right. This was the long step. Did I lose anyone? Okay. So here is where we need to remember what we've talked about with complex zeros. If 3i is a 0, what else is a 0? -3i. I don't know about you, but I don't want to try to factor this mess when I put the x's back. But what we can do, since 3i worked, -3i is also going to work. We're going to do synthetic one more time. With the answer we just got out, we ignore the remainder. Okay, so we're taking the quotient. But this time, all of the i's will disappear. So this synthetic should be nice and pretty. So I take the answer we just got. And now I'm going to divide it by the conjugate, -3i. Okay, so 1 comes down. 1 times -3i is -3i. I's cancel and we get -1. -1 times -3i is positive 3i. 3i's cancel and I get 1. 1 times -3i is -3i. cancels and gives me 0. So remember, this is the remainder constant x and x squared. So we have x squared minus x plus 1. Okay, my directions were to find all the zeros. We have 2 of them so far. I need the rest. Does this factor nicely? No. So what would we do? Quadratic formula. So the opposite of b, plus or minus square root b squared minus 4ac all over 2a. And 1 minus 4, which is negative 3. Square root of negative 3 is imaginary, so you would take out an I. So I asked for all the zeros. We had 3i, we had negative 3i. Imaginary numbers, we do write them in standard form, so a plus bi, so break it apart, so it'd be 1/2 plus or minus I radical 3 over 2. You could write those as 2 separate ones if you wanted. You could put this as plus and minus 3i if you wanted. But we got 4 zeros, and you'll notice they're conjugates. These 2 are conjugates, those 2 are conjugates. Questions on that? So it's the same thing we were doing last week, just if I throw an I in there, it's uglier. Let's try at least one more of these and make sure we're okay. So what do I do first? What do I put here? You have to have those zeros because we have missing power steps. All right, this will be the long synthetic. After this, it will get nicer. So 1 comes down. 1 times negative 2i is negative 2i. Plus 0 is still negative 2i. What's negative 2i times negative 2i? Which turns into? So 3 plus negative 4 is negative 1. So now negative 1 times negative 2i is positive 2i. Plus 0 is 2i. Negative 2i times positive 2i is negative 4i squared, which is now what do we do? Yep. If negative 2i worked, positive 2i will also work. So I'm going to divide by positive 2i, and I'll take the answer we just got out. So 1 comes down. 1 times 2i is 2i. plus negative 2i is 0. 0 times 2i is 0, plus negative 1 is negative. Negative 1 times 2i is negative 2i, and that gives me my 0. My remainder, constant x and x squared. So we have x squared minus 1. Can we factor that? Yeah. Plus 1. That's nice. Okay, my directions were to give all of the zeros. So positive and negative 2i, they're complex numbers, they both worked. What else works? Positive 1 makes x minus 1 equal 0. Negative 1 makes x plus 1 equal 0. Is that okay? Last question of the day, and then I'm going to let you guys work on homework. This is a short question, I promise. Do we need another one like this? No. Okay. So, this is going to set us up for what we're doing tomorrow. If I asked you to find all the zeros and multiplicities of this. No. Oh, it's not that bad. It's factored already. I'm just asking when is it going to equal 0. So it's really saying when does each piece equal 0? When does 3x equal 0? Divide by 3 and you get 0. If you set 4x minus 5 equal to 0, add over the 5 and we get 5 over 4. But that one was cubed, so what's my multiplicity? 3. And we show that with M3. That means 5/4 was a 0 3 times. Okay, if I set x squared plus 3 equal to 0. X squared is equal to negative 3. To get rid of a square, you square root. With a square root, you also add. Okay. So the square root of negative 3, I heard someone say it, is I radical 3. But that was to the 5th, so this would be, let's see, 5. All right, we will do more with that tomorrow. So this is my stopping point for today. There is a handout posted on Google Classroom for you guys to work on. You've got over 20 minutes right now.